Alright, I'm going to start this video as I always do on my test equipment videos with a look at Chuck Penson's excellent book, Heathkit Test Equipment Products. Flipping to the special chapter on the so-called HeathBuilt equipment, which was something that was not listed in the normal Heathkit catalog and was factory-made equipment, distinct for the most part from Heath's normal test equipment. That was made primarily for use in the Malmsted Enke EU-80A laboratory educational program, or the Berkeley lab program that was similar. So again, this is distinctive equipment with the exception of a few models which are just HeathBuilt rebadges of Heathkit equipment and factory built. And the rest are unique equipment that does not have a duplicate in the normal Heathkit product line. I've already got quite a bit of coverage in my other videos on the HeathBuilt equipment, going over all the other equipment in this series. I'm not going to duplicate that again here. So I'm just going to cut right to the chase and go to the equipment of interest. The EU-80A, and notice that all the earlier products in this line were EUW prefixes, or in a couple of instances EWA. They were all pre-assembled, factory-assembled products, but somewhere around the end of the 60s, about halfway through the production of this product line, Heath decided to drop the W designation and they just called them EU instead of EUW. They're still factory-built products. So this is a voltage reference. It replaces the earlier EUW16, which I already have a video on. It's a voltage reference, but not a power supply. It's intended to provide an accurate, stable voltage for instrumentation and experimentation use, but it cannot really deliver any current to speak of, and therefore is not a power supply. That was replaced by the EU-80A in 1969, and that was continued in production through 1976. It does basically the same thing. It's not intended to be a power supply, and as indeed Chuck Penson's note says, this is not a power supply. It replaced the EUW16 in 1969, as I've already said. The 80A provides only 0 to 10 volts in 4 ranges, instead of the 0 to 100 with which you got from the EUW16. The unit features push-button selection of polarity reversal and chopped DC output. It provides sum and difference and calibrator modes. Its stability is 15 ppm per hour. That's part per millions per hour, 1,000 parts per million per month. The regulation gives you less than 0.05% change in output over a 90 to 130 volt power supply range. It came with a voltage to current module that was part of the product line. Oh, my air compressor kicked on, sorry about that. It always comes on just when I'm trying to narrate something. The adapter allows the EU-80A to function as a microampere or nanoampere current source. The unit consumes 10 watts, weighs 4.75 pounds. So I purchased this unit on eBay, also from a seller in the Pacific Northwest in the area around Portland. All my other items in the HeathBuilt line came from a single laboratory in the Beaverton, Oregon area, you know, the home of Tektronix and other companies like that. Whether it was from a lab in a manufacturer's facility or if it was a local educational institution of some sort, that was not disclosed by the eBay seller who had harvested all that equipment from wherever it originally was. Unfortunately, the EU-80A's voltage to current module that should have come with it did not. I'm still looking for one of those. If the schematic diagram shows how to build one. I may build one just to have it complete. Anyway, so I have obtained this unit. I'm in the process of starting restoration on it, and since it has no documentation that I can find in the normal places, I was able to order a reproduction manual from the modern HeathKit company. Much to my surprise, they had it available, and it should come in with a couple days, and then I will proceed to test this equipment and comment further on it for this video. Okay, here's the artifact with the clamshell covers removed. It's remarkably clean, even though the outer case was somewhat scuffed up. There's really nothing wrong with the front panel. It was clean. I didn't really have to do much, but I still wiped it down with some isopropyl and tried to clean the metal inserts a little bit. They had a bit of dust on them. The banana binding posts are pretty clean. The buttons are clean. Going around the back, there's not much there. There are two fuse holders. Again, the type of fuse holders you usually did not see on HeathKit equipment. They tended to put their fuses, if they had them at all, on internal fuse holder clips, and only on maybe some bigger, more expensive things like oscilloscopes did they have external fuse holders. This one has two. One of them is a 0.5 amp slow blow fuse for the line input, the power, and then a 16th amp fuse for the output circuit to protect the semiconductors inside, and a pop-off cover which allows access to an internal potentiometer for calibrating the unit, and of course the Heath label. Doesn't say HeathKit or HeathBuilt, just says Heath. We basically have a big selector switch for the range and a wire wound potentiometer for the least significant digit of the voltage setting, and then selector switches for the two most significant voltage settings. A power transformer with a terminal strip near it. Deep down inside there are there's the mechanism for the radio buttons on the front, and then the circuit board with not many components on it. The trim potentiometer for calibrating. There's a couple of transistors I can see. There are two devices that are metal canned. One of them appears to be probably a dual transistor package. I'm not sure if it's being used as a current mirror or what. And then down there with that heatsink on it is what appears to be a transistor. I'm guessing that's the power output driver, but I don't know yet. There's a couple more transistors down in there. Really just a small number of parts, mostly resistors. Capacitor in there of the, it's probably polypropylene or something like that. It should be good. Shouldn't need to change it. There was an electrolytic capacitor down there where the blue one is now. This is the original capacitor. Callan's 25-128. I don't know if that's the HeathKit part number. Probably is. 100 microfarads at 20 or 50 volts. This type is usually considered to be bad without even testing it, although interestingly enough I did put it on my DCR ESR meter, and it showed a DCR in acceptable range and an ESR of 0.27 ohms, and the normal charts say that 0.5 ohms is good. You want it to be as low as possible, so it's lower than the normal value that's considered to be good. So that was a good capacitor. I did not need to change it, but I did. Couldn't really give it a full test in circuit anyway, so a fresh new electrolytic capacitor of the same ratings is in there. I have given all the switches shots of deoxit, and I've squirted a little bit of lube into the switch mechanism just to make sure it works freely. Let's take a look. Oh yeah, there are 3 neon bulbs, 1, 2, 3, sitting in little rubber bushings, each with a terminal strip next to them that contains, I'm thinking, nope, there isn't a resistor on those. The resistors must be elsewhere. You flip it over on its front, and there's the bottom of the circuit board. Not a very complex one or very large one. Cutouts in the internal chassis prevent the wiring from being shorted out against that chassis. Those things are mounted to the front panel. Sort of an odd arrangement, but not that unusual for Heathkit equipment. They're already starting to do the clamshell cases with this one, and the side rails, like a lot of the test equipment, at least bench-mounted test equipment they had, coming out around the same period of time as this, late 60s, early 70s. A lot of equipment had that. There's my pile of junk down there. There's a Heathkit product from the same period. It also has the clamshell cases, the side rails, and so on. So there's some common thinking between those, and they came out about the same period of time. So what else can we say about this? No other restoration work has been done. I did power it up after I changed the capacitor and did some cleanup, and all the indicator lights worked, all the knobs turned freely, the buttons work. Insofar as I tried them, I didn't try using the chop mode, for example, or the minus source or the A plus source. I haven't tried those yet because I'm not sure how they're supposed to work. I'm waiting for the manual to arrive. So the circuitry is going to be very simple on the circuit board. Very simple power supply, no doubt. Very few semiconductors. A lot of the work is being done by all these precision wire-wound resistors that are around these switches. Some of them down there too. So again, I did turn it on, I powered it up, and I was able to go through the full range of outputs. And it basically is working at this point, but I'm a little confused by the switch here because it changes which of these 3 indicators are on, and it says millivolts in each of those, and then one of the positions says volts. So 1 volt and 3 millivolt position. I don't know the significance of these lights. I'll find out when I get the manual. When I did my preliminary test, I found that the output was open. Even pushing the 0 button on the front was not shorting it, so I just had my digital multimeter floating around at various readings, just picking up signals from the air. And I reasoned that the output fuse was probably blown, and sure enough it was. The 1/16 amp fast blow fuse was in fact open. I didn't have any more even close to that, so I've ordered a box of those from DigiKey, and those should arrive tomorrow or the day after. I did test it just with a jumper wire across the fuse, since I was sure I wasn't shorting the output out, and then it did come alive and start working. It does need calibration. One other thing I did for restoration on this was the 2 clamshell case halves are just pinched to the side rail with a couple of screws and washers on each side. And these, I think they're zinc plated steel screws and washers. They were really powdery. They tend to oxidize in a way that leaves them covered with sort of a white powdery gunk on them. And so I cleaned them in vinegar for about an hour, scrubbed them off, and then used a polishing wheel on my Dremel to just give them a bit of a shine back again, and they're looking pretty good. I don't need to replace them. Here's a preliminary test. I've tweaked the calibration potentiometer with it set to 100 millivolts, and I've turned this control until this LED is on. I'm supposing at this point that's supposed to be where the decimal point is, and it's kind of positioned in that way. It's to the lower right of the numbers, so assuming that's right, and I don't have any of these other things engaged, it's sitting there just below 100 millivolts at the moment. It did sag a little bit since I adjusted it. I'm kind of curious what the zero output on here gives me. So it's favoring it by 0.21 millivolts. So I really should be adjusting it for 100.21 millivolts. Okay, I got it somewhere in that ballpark. Now what if I change the decimal point to here? Then it would be 10 millivolts, right? Well, now 1 millivolt. Pretty close. And I'll change it so we get that decimal point. It should be 10 millivolts. So that's what that switch does. And the indicators indicate where the decimal point is. So that's your range control. And then finally, of course, I can go to volts, where it'd be 1 volt now, and really close. And if I crank that up to the 9 on here, it's really close to 9 volts. It's sagged a little bit. And I'll crank this guy up to 9. And we're a little bit low. And I'll crank this guy up to 10. So that should be giving me 10 volts. So I'm going to recalibrate it to have that be 10 volts, with the assumption being, like the other voltage reference, you were supposed to calibrate it at the highest voltage output because everything else is resistor divided down, and you want to test without the resistor dividers in there. Okay, with this still set to 999 plus 1, so well, as close as I can get to 10. Let's see, is that really right? 99, and it would be 9, but it's rolled over to 1, so that rolls up to here. So that should be 10 volts. And it is 10 volts exactly now. Now if I crank down the range here, now it should be 100, or that's 1 volt, yeah. So 1000 millivolts, yes, 1 volt. Air compressor picks that time to come on again just when I'm trying to talk. Now 99, essentially 100 millivolts. It's a little high, but probably within tolerance. And now 10 millivolts, but it's reading 20 for some reason. Why is it reading 20? That's really weird. Huh. I got no idea why it's doing that. Shouldn't be able to give me 20. It could be there's an error in this thing that it's giving me, like, you know, twice what I expect to have there. Don't know what that is. Let's turn this guy down to 0. Yeah, it's not affecting the output at all now. Oh, it is a little bit. So now it should be 9 millivolts, and it's 17. That's weird. I'll have to read the manual when I get it to see if there's some exception to this. I don't know what these two modes do yet. I don't know what the chop does. Again, I'm waiting on the manual. It should come tomorrow sometime, but some progress is being made in figuring out how this works. Alright, let's just do the quick demo. I've double checked the calibration again. I'm at set to 9, 9, 10 and volts. So that should be giving me 10 volts. So it's 9.9 and then 10 from that position. It adds up, so it rolls over to 10 volts. And I'm getting 10.01 volts on the meter, which is about as close as I could hope to get. If I crank this guy down to 0, it's taking me down to 9.9 volts very accurately. If I bring this back up to 10 and go to 8 on here, well, I need to take this to 0 for that to work. 0, 8. There. 0, 7, 6, 5, 4, 3, 2, 1, and basically 9, which I'm getting here, 9. And then 7 or 8, 7, 6, 5, 4, 3, 2, 1, and 0. And that's the same quiescent voltage I always have with this meter. If I push the 0 out button, it's going to fall down because it's not supported well on my wood block. If I push 0 out, it's going to take it down to around 0.2 millivolts. Okay, so let's go back up to the full output here. And once again, I've got 10.000 volts on there. I'm going to go to the next position, which is a millivolts reading, and the decimal point's over here. So it should be 100 millivolts, 99 plus 10 in the least position. Decimal point is showing up here. Right, so it's giving me 1 volt there. So again, if we roll this up, it's 1000 millivolts, so that is 1 volt. And I'm going to take the knob down to 0. So now it should be 990 millivolts, and it's still showing me basically the same thing. If I go to 8 here, and I can select it down. So now it should be about 900 millivolts. 900. And if I take that down, 8, 7, 6, 5, 4, 3, 2, 100 millivolts, 100 millivolts, 0. Still with that quiescent amount over there in the least significant. If I turn this range knob one more time, now it's going to move the decimal point to here. So if I start cranking up here, I should only get up to 100 millivolts. Let's go to 10, 20, 30, 40, 50, 60, 70, 80, 90, and then start bringing up the next digit. 2, 3, 4, 5, up, 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 up. So we've got, it actually is a little less accurate here because we're getting down into the further resistance ranges. So we're adding tolerances of resistors. This should be reading 100 millivolts, and it's reading a little high. Again, that's resistor tolerances. But I believe it's within spec because it's plus or minus 1%. It should be 100 millivolts. Taking away the quiescent 36 millivolts, that's just the meter, it's really at 1% of what it should be, so it's okay. I'm going to turn it one more time to the remaining range. So now it's going to be up to 10 millivolts. 0. And again, it's off by like 1 millivolt there. Reduced accuracy. So I'm not getting really good results here. There's probably one resistor in there which is kind of off. That's affecting it when it's in this lowest range. Alright, so this guy's underperforming on the lowest range. The same switching is involved, so I don't think there's actually a problem with the switching. I think it's just some resistors are a little out of whack in that range. And I'm not going to mess with that at this point. Now the other things we have here, we have the ability to chop the output. And as I've learned since I have the manual now, the circuit derives a tap off the power transformer secondary and then runs it through a Schmidt trigger to square it up. So you have a 60 Hertz square wave, and that's used to modulate. It's essentially like pushing the 0 out button in and out at a 60 Hertz rate. To see that, I'm going to have to hook up my scope. Okay, I have my scope set up so it's on 5 volts per division with ground being there. So it is set to read 10 volts, and it is showing me 10 volts. That's 5 plus 5 is 10. And if I engage the chop button, now I get a square wave. The irregularity in the intensity there is just an artifact of the camera. It's not really brighter in some spots than others to the naked eye. But so that chop function's working just fine. Take it out of chop and it returns to the normal DC. Okay, to check the sum and difference modes, I have my bench power supply set to 8 volts and it's connected to the A input terminals, but I'm not engaging that yet. I will turn it on, and I'm still not engaging it, and it doesn't affect the output, which is sitting there at essentially 10 volts, which is what it should be. And the scope is also showing 10 volts. Now, this minus S here, S is supposed to be source, meaning this device, so pushing the minus S does not engage the A input. Instead, it flips the polarity of the output. So that should take me to minus 10 volts, which is what I've got, and the scope shows the same thing. So I'll take that out, return it to positive operation, and now when I push the A plus or minus S button, that will put the A input and the output of the source in series. So right now with a 10 volt here and an 8 volt there, I should get 18 volts if I engage this switch. And I do. 17.998 volts. That's working fine. Now if I invert the polarity of the source, it takes me down to 2 volts, minus 2 volts actually, because it's giving me minus 10 in series with plus 8, so minus 2 volts. Take the minus out, we're back to 18 volts, and that plus and minus function is working fine. So I would say, except for some glitchiness in the lowest millivolt range, this is working perfectly. Alright, I think I've tracked down the problem on the lowest volt range. It depends on this function switch, and it looks like there's a cracked wafer on here, and the couple of the contacts aren't making really good connection. I don't think I can feasibly fix that, so I'm just going to let it go as is. If I was actually going to use this on a regular basis, I might take it apart further and try to fix that, but since it's working 100% in every other regard, I'm going to let that go. Well, I did go back and super glue the cracked wafer, and that wasn't really the problem, although I thought it might have contributed to it. And then I was looking at the schematic and calculating all the permutations with all the parallel resistances in the whole divider network, and I found that a resistor that they identified as being 49.95 ohms was mismarked, and it had to be 49.95K to work out correctly mathematically, and the actual resistor installed was 536 ohms, just like a totally wrong part. So I took that resistor, and because it's almost inaccessible back there, and I cut its lead where it goes onto the switch and interjected just a regular 1% 10K resistor in a trim pot, and I've got it dialed in. It's jumping around between 10 millivolts and 9.99 millivolts, but basically there. And if I take the control, the most significant control here, and start dialing it down, I get 9, 8, 7, 6, 5, 4, 3, 2, 1. So that's working now. And then if I go to my other ranges here, I should be able to get up to 100 millivolts, and the next range 1000 millivolts or 1 volt, and the highest range 999.6, essentially 10 volts. So this thing is working now, and it's all because of one resistor that was grossly the wrong value, which meant this thing never worked on its lowest range, straight from the factory. And they have a misprint in the schematic that says it should be orders of magnitude away from what it really is. Well, these sort of eggshell or ivory colored outer case halves, in a departure from the earlier kits in the series, instead of just having a sort of a flat, smooth surface, they got the kind of wrinkle finish like a lot of Heathkit equipment from the 70s had, so they were kind of getting into that style. Now, like all the other HeathBuilt equipment, the feet are riveted on instead of screwed on, or adhesive feet. They do have the kickstands for the front feet, but these are kind of banged up. The bottom isn't as bad, obviously. The top has got missing paint and scratches and other things that may not show up too well in the picture. But I've decided to repaint them, and I found this Rust-Oleum 2X paint and primer. It's called Heirloom White Satin, and even though it doesn't look like it so much in the camera, when I was doing the comparisons in the store, that was a pretty close match. So first thing I'm going to do is put it in the warm soapy water, give it a little soak, scrub it off, and then give it a shot of paint. Washed, scrubbed, and drying with the heater fan. Alright, ready for spray painting. And once again, I'm using the Rust-Oleum 2X paint and primer in the Heirloom White Satin color. Alright, one coat of paint drying under the heater fan. I decided to wash the knobs and banana binding post knobs. So I had soaked them in warm soapy water and brushed them off with a toothbrush and touched them up with the cotton swabs with isopropyl alcohol on them. I'm just waiting for them to dry now and they can go back on the instrument. Here are my two freshly painted clamshell case halves, and I'm going to put them on the chassis now. Okay, there's the beauty shot. Alright, let's take a look at the manual. Now this is interesting. There's a company called, I think, Data Professionals out of California, and they've been selling a number of little kits and replacement parts for vintage Heath kits. You know, new anemometers for the weather stations, little circuit boards that replace the displays that fail on some of the old, you know, ham and stereo equipment with newer technology displays, things like that. They also sold Heathkit manuals for a lot of the products, reproduction manuals. I'd heard that that was the company that ended up becoming the modern Heathkit company, but then I heard it was a completely different outfit, so I'm not really sure. I was going to Chuck Penson's website where he mentioned that, you know, while Manual Man and some of these other sources have a lot of Heathkit manuals, they do really beautiful reproduction manuals. You know, with everything all cleaned up digitally and really, you know, excellent reproduction, that the old Data Professionals still provided a lot of manuals that weren't available anywhere else. So I went to the website, and the actual invoice that came from the company when I ordered it online has the Heathkit logo, and it says Heath Company Vintage LLC, Dublin, California, and it has the D8A Pro URL on there, and the manual itself uses the same modified artwork that is on the modern Heathkits manuals, at least based on the so-called most reliable clock that's, in my opinion, the only real product that the modern Heathkit company has, and has had 10 years of production on that without really introducing anything else. But they've changed the old artwork to have a girl doing the work instead of the boy that used to be here, and they've changed the little picture of the radio that was there before into their current AM radio, which is kind of a joke kit, really. You know, it isn't that great. I don't know why anybody would want to buy it, but anyway, so it's kind of interesting. I'm not sure if this Heathkit's working in parallel with the modern Heathkit company, or if it's a branch of it, or just some sort of affiliation. Not clear. Anyway, so it's decently done, but it's not as good as the ones coming from manualman.com. It's not cleaned up. It's got all the warts and things, and it has, you know, earmarks of having been Xeroxed a few times before it was, you know, reproduced here. But, okay, so we've got the picture of the product along with its included voltage to current accessory, which was missing from the one that I bought and probably is missing from almost anyone you can find. But according to Chuck Penson's book, it is supposed to be part of the product. And the table of contents. Specifications. Output voltage is 0 to 10 volts DC regulated. The readout is directly indicated by 4 dials viewed through panel apertures. Voltage accuracy, you have to look at a table to get that figured out. And that table's over here. So the most significant digits has a 0.1% tolerance. So does the next, but this digit has a 1% tolerance. That's because it's a potentiometer where these are switches selecting in 0.1% resistors. So the pot itself is not going to be as accurate, and just, you know, because it's a pot and not discrete points, you know, you probably can't dial it in visually any closer than 1% anyway. Voltage stability short term 15 points per minute per hour. Long term is 1000 points per minute per month. Voltage regulation output potential will vary less than 0.05% with a change in line voltage from 90 to 130 volts AC. That's assuming you've got it wired for the 117 or 120 volt arrangement. It can be wired to run off of 200 to 240. With the voltage to current accessory, you can get up to 10 microamps in one position of the switch and 0 to 10 nanoamps in the other position of the switch. And that's based on setting the actual voltage reference in its 0 to 10 volt range and then using it with that accessory to get those currents. Output accuracy, we've already talked about that to some degree. The four ranges are 0 to 10 volts, 0 to 1000 millivolts or 1 volt, 0 to 100 millivolts, and 0 to 10 millivolts. Neon lamps indicate the decimal point where that should be out of the 3 digits and the range. The voltage selectors use 10 position Kelvin-Varley voltage divider switches for the first 2 digits and continuous adjustment via potentiometer for the 3rd digit. There are additional switches, just like on the other voltage reference that I already did a video on, the older version of this product really. You can still bring in an external signal and add it to the internal voltage reference, either with the same polarity or opposing polarity. Therefore, you can make it into an adder or a subtractor or a difference. It'll find the difference between the two signals or add them together. And you can also chop the output. It's possible to modulate the output at whatever voltage you've set it to between 0 volts and that set voltage in a square wave 50% duty cycle chopped pattern at a 60 hertz rate. It works off the power line. If you're running it off of 50 hertz power, then it'll modulate it at a 50 hertz rate. There is a plus S minus S push button which allows you to change the polarity of the source potential coming out of the output binding post. There's a 0 push button to short the output leads together. And there's one calibrate control. This is a lot less fussy than the other one, which had calibrate control for the voltage, and then you had to dial in the proper current for the Zener-regulator stage and the voltage regulator tube stage. So all very iterative and takes a lot more time. This one's much nicer in that regard. It can operate, it takes 10 watts, whether it's in the lower voltage or the higher voltage input range, and it weighs about 4 3/4 pounds. Introduction. The Heath model EU-80A voltage reference source is a very accurate, regulated variable DC voltage standard designed for maximum convenience and versatility. The push-button function switches select the mode of operation, permitting the voltage reference source to be used as a DC voltage standard, a 60 Hz signal source for oscilloscope calibration, or a precision DC sum or difference source for voltage comparisons, potentiometric measurements, and bucking voltage applications. 3 direct reading voltage controls and a range switch on the front panel vary the output of the reference source from 1/10 of a microvolt to 10 volts. The proper decimal point position for each range setting is indicated by one of 3 neon lamp decimal points. The polarity of the reference source output may be reversed by the plus S minus S push button. A chopped DC output in the form of a 60 Hz square wave is available by pushing the chop S push button. The peak amplitude of the square wave will be equal to the DC output level set by the voltage controls and range switch. The DC voltage standard is very useful for calibrating meters, recorders, and other readout devices. It also has many applications as a voltage source for operational amplifier circuits, which serve as constant voltage sources, constant current sources, comparators, and controllers. When the A plus or minus S push button is pushed in, the potential at the output binding post is the sum of or difference between the signal voltage applied to the A input binding posts and the voltage you've set for the reference source. If a meter or recorder is connected to the output, the voltage reference source can be used to buck out unwanted portions of the input signal. A potentiometric measurement of the A input signal can be made by connecting a null detector to the output and properly adjusting the reference source. When the null detector reads 0, the A input signal and the reference source are equal. This is a very accurate method of measuring voltage because changes in voltage due to loading are eliminated since no current is drawn from either the A input circuit or the reference circuit at null. With the spring-loaded 0 out push button, when that is held in, it will disconnect one of the internal source output lines from the common output binding post. It will also short together the common and the positive output binding posts. This feature is especially convenient when the voltage reference source is being used as a calibrating source or when checking the null position of potentiometric measurements. A voltage to current accessory is also provided so the voltage reference source can be used as a microamp or nanoampere current source. This accessory plugs into the output binding post and places a precision 1 megohm or a 1 gigohm resistor in series with the output. This kind of high resistance current source is very useful as a precision source or calibrator for low resistance or virtual ground circuits, which are often encountered when operational amplifiers and servo systems are worked on. This instrument is one of the units included in the Malmstat Enke EU-80A instrumentation laboratory. It is available as an individual unit or can be purchased at a special group price when included with the total EU-100A system. The units of the complete EU-100 laboratory station are useful not only in learning electronic concepts but also in research and development and control instrumentation. Then we get into the operation part of the manual telling you how to use it. It talks about accuracy, impact by load resistance. You are not supposed to have a very high or very low load resistance on this. It's not really a power supply. It's very limited in its ability to provide current output. So it really should go into high input impedance circuits. Interestingly, the manual's specifications page does not mention the loading resistance, but this page does. So if you're in the 0 to 10 volt range, you need to have an output load no less than 500 ohms in order to keep the reading accuracy within 0.1%. If you're in the 1000 millivolt range or 1 volt range, the maximum or the minimum load is 50k ohms. And the same as if you're in the 100 millivolt range, also 50k. And if you're in the 10 millivolt range, then you should not have less than 60k ohms on the output. All of those will assure that the reading output, or the reading and the actual output, are within 0.1% of each other. There's some application notes here about chart recorder calibration and linearity checking, multimeter calibration, operational amplifier reference voltages, recorder offsetting. So you want to bring in a signal source, but you want it to be offset, and you can put this in series with it and thereby provide an offset voltage, either in a positive direction or negative direction. And then potentiometric measurements. So if you only have a null indicating meter and you don't have a precision voltmeter, then you could take whatever signal source you're trying to measure, bring it into this unit, adjust the voltages on here until the meter reads null, and then you can read the voltage off the front panel, and that will be the voltage that you're trying to measure. Talks about using the chopped DC output that's useful for calibrating oscilloscopes and other stuff. With the voltage to current accessory, you can use it to calibrate or check current measuring devices, such as microammeters or other current measuring devices. Then we get into the circuit description, which I'll talk about using my own analysis of it. Several pages on that. This is actually has a fairly decent description. There's a in case of difficulty section, 1 page, and a troubleshooting chart. Replacement parts list over at least 2 pages, going into 3 pages. There's a chassis photograph primarily of the top of the circuit board. Really hard to make out on here. The photo is way too dark. There's the X-ray view of the bottom side of the printed circuit board. And then there's the note on how to move jumpers on a terminal strip to select 105 to 125 volt AC wiring or 210 to 250 volt AC wiring. So the 2 alternate wiring methods. And there's connections for determination of minimum allowable load resistance. And then there's an appendix talking about how to calibrate this unit, and if you need to convert it from one line voltage to the other, tells you how to go about doing that. And then the schematic diagram, for some reason in this reproduction, it just gives you a little piece of the left side of the schematic that's not very useful. That's something manualman.com wouldn't make that kind of blunder. It's just attention to detail is not that great, and then you're at the back cover. There are 2 fold-out diagrams which are reproduced here as separate sheets. There's the chassis breakdown. It's not really an assembly diagram, but it's kind of a identifier of all the screws, hardware, switches, and what everything is, so you can look at it on here and find it on the replacement parts list by all the numbers that are on here. So that's really what that's for. It's not an assembly diagram. And then there is a diagram of the voltage to current accessory for the same reason. All the parts can be purchased as replacement parts as need be. And I should mention that since I did not get the voltage to current accessory with mine, I just read up everything that was in the manual and realized that it's really simple, but they had a shielded metal box, so I had to get a shielded box for the one that I'm fabricating. It has a slide switch of a particular type and size. It's a little tricky to find those anymore. They're not very common. But Janeco came through on that. An insulated BNC connector, 2 high precision, high resistance value resistors. That took a bit of digging to find suitable ones of those. And then Pomona Electronics comes through via DigiKey for these male banana posts that stick out to go into the plugs on the front panel of the device. So I will do a separate video once I get all those parts and have that built. And then there's the front panel and rear panel explanation diagram that goes along with the operating instructions. It just identifies the A input, the output, the 5 switches, one of which is a power switch and the others are various mode switches for sum and difference and polarity swapping, zeroing the output and chopping the output. And then the 2 Kevin Varley divider control knobs, the potentiometer control knob for fine adjustment, and the range switch. And the 3 decimal points that are provided by neon bulbs. and then the rear, which has the fuse holder for the line power and the fuse holder for the output, and the little cover for the calibrate. Okay, here's the schematic diagram. Since it's fairly neatly drawn, I'll go through it without, for the most part, referencing my own sketches, but when I start explaining this area, I will use a sketch that I made. So you start out with the AC power, and there is a version of the diagram for the 220 volt wiring. It has the line cord coming in, the grounded pin goes to the chassis. The old version of this just had a 2-wire connector, and the chassis was not connected to earth ground. There's a fuse to protect the circuit if this fails and draws too much current. There's the 2-pole power switch. It interrupts both the hot and the neutral. And then you have your 2-winding primary winding, which can be wired in series or parallel. It would be wired in series if you're using the higher voltage option, but you have the 2 coils wired in parallel if you're running it at 120-ish volts. The 3 neon bulbs, which function both as decimal points and also as the power on indicator, those need to be run off of just the 120 volts. So if you are in the 120 volt power wiring option, the selected neon bulb and its current limiting resistor are just wired across the whole transformer, so it gets 120 volts. And then this current limiting resistor is appropriate for that much voltage to get the right amount of current through the neon bulbs. But if you're in the 220 volt wiring arrangement, it actually treats the middle of these 2 windings like a center tap. So while you may have 220 volts applied across the entire transformer, at the center tap there's only 120 volts, and so that's used this way so they still see the neons still see the same voltage regardless of which line voltage you're running the unit at. The power supply is pretty simple, otherwise I'm trying to avoid getting a big shadow on this. Sorry about if I do. So you have a center tap transformer. It's supposed to be about 36 volts center tapped. It has 2 diodes, and they're connected up as a full wave rectifier, but it's not a bridge, and you can get away with that because the center tapped is connected to the circuit ground. There's a single filter capacitor, 100 microfarads at 50 volts, wired across that, the output of the rectifier, that is, and that is applied to this circuit, which is a classic linear power supply circuit. So this is the pass transistor, and because it needs to have more gain than it does, this other transistor is used along with this in a Darlington pair. So you the gain of this transistor is coupled with the gain of this transistor to make the gain of the pass transistor higher than it would be by itself, but that's why that's there. In order to make this conduct, you have to have some base current going into it. So this FET is wired up as a constant current source, so it'll put out a certain amount of current coming out here. It just taps it off the unregulated side of the pass transistor, and you get a current that doesn't change pretty much no matter what. And ordinarily it only has 2 places for that current to go. It can go into the base of this transistor, which then controls the base of this transistor and controls how much it turns on to let the power through to the output of the voltage regulator stage. And some of the current also goes through this transistor, through this resistor, back to circuit common, or ground if you will. Not chassis ground, but circuit ground. So there's 2 paths. Some of the current goes this way, some goes this way, but it's always the same amount of current that gets split between them. It cannot increase or decrease. If this amount of current goes up, then this amount of current must go down, and vice versa. Alright, so how do we get the regulation? Well, we do it with essentially an op-amp of sorts, at least a differential amplifier made out of these two transistors which are in a single housing, so they operate at the same temperature and they track each other very well. They have a common emitter, which has a resistor going back to circuit common, and you have a Zener diode here with a it's coming off the regulated side of the pass transistor, and this resistor is calculated to provide the optimal amount of current, which is 7.5 milliamps, through this Zener diode, at which current it provides its most stable and accurate voltage of 6.2 volts at this point. So you have that applied here. That causes a certain amount of gate current in this transistor, which causes it to turn on a certain amount. And because this is a differential amplifier, if you have more current going this way, then there's going to be less current going this way. You also take the output voltage as it exits the series pass transistor, and you go through a big voltage divider back to circuit common. And these two resistors just limit the span of this calibrate potentiometer. This is about 5K, this is about 10K, and this is only a 500 ohm resistor, so the vast majority of the output voltage, which should be 10 volts always, the vast majority of that voltage is dropped by this resistor and this resistor. Just a tiny amount is in here, so you can crank this around and get some pretty good accuracy. You control how much voltage is applied here, therefore how much current goes this way, and that is compared with the voltage here, and between them it determines how much current is drawn this way. So when you draw more current this way, that means there's less current going this way. If there's less current going this way, then this transistor shuts off some, which makes it have higher resistance, which means the output voltage will decrease. If the voltage here decreases, then the base current on this guy is lower. It's conducting less, therefore it's stealing less current from here. Therefore the current that's available to go this way increases. The transistor turns on more. It has less resistance, and therefore the output voltage increases. So that's how that works. Fairly classic feedback arrangement for a linear regulator power supply. Now this is not a power transistor, it's just a small transistor with a heat sink on it, so it is limited to very low currents, but all the current going out here is pretty low, so it's able to deal with that. Now what's this doing over here? Well, you also tap off the secondary winding of the transformer through a diode, which turns it into a half wave, and that is applied to these two transistors that act like a Schmidt trigger. So they provide a snap action and a threshold, so that what would look like a kind of a lumpy half-wave rectified signal coming in here gets turned into a nice 50% duty cycle square wave coming out of this point. Of course, it's not generating that, but that's essentially what you would see here. So this provides another path for this constant current. Now it can go here, and some of it can go here, and some of it can go here. But this is not turning on and off a little bit like this is. This is like fully conducting, or it's not conducting at all. It's like a switch. So when this transistor is turned off half the time of the square wave, then it does nothing. It doesn't influence this at all, and the output is whatever it should be, which is 10 volts before all the dividing, but 10 volts at this point. But then when the transistor turns on fully, all the current coming out of the constant current source is going this way. None of it's going this way, none of it's going this way. So this resistor, or this transistor, turns off entirely, and therefore the output voltage drops to zero. and it goes back and forth toggling between the proper 10 volts out here and 0 volts at the 60 hertz rate, giving you a square wave type signal of 10 volts out at this point. Of course, if you attenuate it, then you can have it be much lower voltages for that square wave. So there's a 3-stage attenuator here done with voltage dividers, and I'll go into that in a moment. The output, very similar to the other reference that I did a video on here shortly ago. It's almost exactly the same circuit. You have a 2-position switch which both disconnects the output of all this stuff from the output terminal, and it also shorts the plus and minus output terminals together, so you're assured of providing 0 volts, but you're not shorting this circuitry out in the process, only shorting the output terminals together. So that's useful. There is the I was pointing at this switch, but it's really this switch which is doing the zeroing. Sorry about that. This is the switch that A, disconnects one side of the power supply from the output terminals, and B, shorts the output terminals together, although with the fuse still in there to protect it. This is the switch that reverses the polarity, so in one position this plus output goes to the plus terminal, and the circuit common goes to the minus terminal. If you push the switch the other position, the positive voltage here goes to the minus terminal, and the positive terminal goes to circuit common, or 0 volts. So you effectively flip the polarity of the output. Then this is the A plus or minus S, where A is the external signal that you can apply, and S is the voltage generated by all this stuff over here. So you can either put, well, you're always putting the two of them in series when you push this button. It puts the externally applied signal, which is cropped off here. I'll mark that back in. Input, output. So you can optionally apply that external voltage. It can be positive or negative. And you, by pushing this switch, you can put it in series with the voltages coming from here. And if they're both of the same polarity, then they're added together. If they're of opposing polarities, then they're subtracted from each other. Therefore, you're finding the difference between the two voltages. So that's very common and cut and dried. So now let's take a look at the range switch. The range switch circuit is right here, and it goes between the output of the voltage, regulated voltage section of the circuit, and the 3-stage attenuator for controlling the output voltage. This just controls the range in 4 orders of magnitude. So to make that a little clearer, I have redrawn it here. So you have 3 gangs, 1, 2, and 3. Each of them are 4 positions. You've got the 10 volt position, the 1 volt or 1000 millivolt, the 100 millivolt position, and the 10 millivolt position. And that's the same for all of these. And then that has some resistors, and some more resistors, and another resistor down here. Now, it's important to keep in mind for this that everything over here, the fine potentiometer, a parallel resistor across it, and it's across part of the middle position of the divider, and it has a single resistor across all of it. So this resistance is across 2 resistors of this. This is across the entire resistance of this, and then that whole resistor, all of this stuff, gets put across the 2 of the resistors of this guy. And in addition, the entirety of all of this can have a resistor value put in parallel with it, as well as in series with it. The top part of the switch puts series resistance in, and the bottom part down here puts a parallel resistance across it. So we're going to look at that here with my sketch. If you're in the 10 volt range, the output of the regulator comes straight through the switch and right into the Kelvin-Varley attenuator circuit. So you get the full 10 volts applied to all the attenuators, in other words. But if you bring in the 1 volt range, or the 1000 millivolt range, or the 100 millivolt range, or the 10 millivolt range, you add resistors in series. Now you have to go through this resistor on the way out, or this resistor on the way out, or this one on the way out. And in addition, on the two lowest ranges, we switch in these two resistors going back to circuit common. And down here I penciled in a 500 ohm resistor, which is effectively what all of that downstream stuff adds up to, and it's always 500 ohms no matter what you have them selected to. That's the way the circuit is set up. That's why it's a Kelvin-Varley attenuator. That's the definition of it. It's an attenuator that presents no change in resistance or loading to the circuit upstream from the attenuator. So I put that in here just for the sake of reminding myself that everything downstream is 500 ohms. And sometimes you put another resistor in parallel with that. A little 55.5 ohm resistor can get put in parallel with all of that. So let's talk about how that works. So here's the equivalent circuit if you're in the 10 volt range. The output of the regulator comes straight through the switch and goes down to the Kelvin-Varley attenuators. So the full 10 volts is applied to the attenuators. In the 1000 millivolt or 1 volt range, you still have the 10 volt coming out of the regulator, but now you introduce a 450 ohm resistor in series with the Kelvin-Varley attenuator, and you put a 55.5 ohm resistor across the Kelvin-Varley attenuator. If you do the parallel resistance formula for 500 ohms in parallel with 55.5, it comes to 49.95 ohms. If you do Ohm's law on this circuit, you find out that that gives you exactly 1 volt across the Kelvin-Varley attenuator. So now you've turned 10 volts into 1 volt. And that's appropriate for that 1000 millivolt range. Now if you go into the 100 millivolt range, it's similar, but now you have a 4.95K resistor upstairs, and you still have the 55.5 ohm across the 500 ohm of the Kelvin-Varley attenuator, so it's still 49.95 ohms in series with the 4.95K resistor. You do the math, and it comes out as 0.1 volt here, in other words 100 millivolts. And I'll talk about this extra resistor in a minute. So in the 10 millivolt range, we just changed the upstairs resistor to 49.95K, while the downstairs stuff still is 49.95 ohms. Do Ohm's law on it, and you do in fact get 0.01 volt or 10 millivolts. So all of that adds up exactly right. Now, if you're looking at these two higher ones, the resistance load presented to the voltage regulator circuit, a voltage regulator circuit won't work unless there's some kind of load on it, and a lot of them have a built-in load of some kind just so there's current flowing through the circuit. If you're in the 10 volt range, then you have the 500 ohms of the Kelvin-Varley circuit as a load, so it's perfectly good with a 500 ohm load. If you go into the 1000 millivolt or 1 volt range, now you take the 500 ohms of the Kelvin-Varley circuit, but it's reduced by 55.5, so it's only about 50 ohms. You add that to a 450 ohm resistor that's introduced by the range switch, and guess what? 50 ohms plus 450 is 500 ohms. The regulator still sees the same 500 ohm load, just like it would appear when the Kelvin-Varley circuit is the only load on the voltage regulator. And the same thing works out down here. If you're in the 100 millivolt range, now if you add this out here, you've got 4.95K in series with 49.95 ohms. Obviously, that's a huge step up in load resistance. That's not appropriate. We want to present as much of a constant load on the voltage regulator as possible. So how do we achieve that? We put a 555.5 ohm resistor in parallel with all of this stuff, and that effectively knocks the resistance down to close to 500 ohms again. As far as the voltage regulator is concerned, it sees a resistor of roughly 500 ohms with all this other stuff combined. Same thing happens if you're in the 10 millivolt range. Now you've got 49.95K in series with the 49.95 ohms of all the attenuators, but you put a 505.05 ohm resistor across it, so it adds up to the same thing it's expecting. It's seeing approximately 500 ohms. So that's why these two resistors here are added. That's what these two resistors in this middle gang of the range switch are doing. Now, having said that, I think I touched on it elsewhere in this video, but on my example of this product, everything worked great except for the 10 millivolt range when I was getting some pretty screwy output voltages. And I reasoned that it could not be the Kelvin-Varley circuit doing it, or the output switching circuit for the sum and difference and the polarity changing. Those all were tested already in the other voltage ranges, and they were all working fine, so there's no incorrect resistors or bad switches going on there. It has to be something in the range switch. So the first thing I checked was, is something dragging the output of the regulator down? Is it being shorted out somehow so it can't provide the requisite 10 volts? No, that wasn't happening. So that means either a fault in the switch, the range switch, or one of the resistors, and obviously the one for the lowest range. The HeathBuilt schematic called the resistor for that 49.95 ohms. That's on the schematic, but the parts list says it's 49.95K. So they meant 49.95K, and that is correct. But when I measure that resistor, and the way I had the switches set up, that resistor was out of the circuit, so I could measure it reliably with my ohm meter, and it was actually 536 ohms. So way, way, way off of the 49.95K it should have been. That explained the problem. And essentially what I did is I took this resistor here and added, I just cut the lead so it didn't go back to the switch here. I introduced it right here by cutting this lead, and then I introduced a fixed resistor and a potentiometer that together added up the difference to get it to approximately, with the potentiometer in the middle of its range, the whole thing added up to approximately 49.95K. And then I could just dial in the pot and fine-tune it, which is what I did, and that worked fine. So I have no idea why that resistor was so low. I'm guessing somebody just grabbed the wrong part in the factory and installed it, because obviously Heath intended the correct value to be there. It's on the parts list, and just a drafting error left off the K on the schematic. But that tells me that when HeathBuilt built this product in their factory, they had the grossly wrong resistor in there from the get-go. There's no way they could have tested it in all four ranges and got the correct result with that resistor. So obviously their quality control was somewhat lacking there. Maybe they only did a perfunctory check of the highest range or something and assumed the rest was fine, but that's kind of embarrassing for them. Anyway, it's not a fault of the circuit, it was just a fault of an incorrect component soldered in at the factory. So now let's take a look at something I did not sketch, and that's the two Kelvin-Varley dividers. Now it's the same circuit as on the other voltage reference that I did my previous video on, except that one only has a single stage Kelvin-Varley and then a potentiometer. This has a two-stage Kelvin-Varley with a potentiometer. But it's the same circuit. The only thing that's different is the resistance values in each stage are different. These are only 50 ohms per stage of the resistor divider, or I think they were 500 ohms or 400 ohms, something like that on the other one. That one has very much less ability to drive current than this product does, so it needed to keep those resistances pretty high. Because it's a Kelvin-Varley divider, the resistance it provides to upstream circuitry has to remain unchanged. So unlike other voltage dividers where you're tapping off at some point in the divider, on the Kelvin-Varley one, you've always got one more resistor than there are positions. So there's 11 resistors of 50 ohms each, but the switch around the attenuator presents the downstream resistance across two of those resistors. So you're always putting the output circuit over here across two of the resistors, or maybe it's these two, or these two, or these two, all the way down the chain until you can have it across the bottom two resistors. And therefore the overall resistance never changes. It's always taking all this downstream stuff looks like a 50 ohm resistor with all the parallel resistances. It looks like 50 ohms, and that never changes because everything downstream is also a Kelvin-Varley. So this is always 50 ohms, and it's across two resistors that are 100 ohms together, if you add them together. I'm sorry, I said that wrong. These two resistors in series, in parallel with this 125 ohm resistor, in parallel with this entire second stage Kelvin-Varley, including the 200 ohm fine potentiometer, which is in parallel with a 200 ohm resistor across it, and that's in parallel with two resistors of this second stage Kelvin-Varley. All of that stuff adds up to 50 ohms. So it's not 50 ohms in parallel with these 250 ohms in series. This whole thing, including these two resistors, all adds up to 50 ohms. So you've essentially taken two 50 ohm positions of the divider and turned it into effectively a single 50 ohms. So you, instead of having 11 50 ohm resistors, it's like you had 10. And that is, of course, you add up 10 times 50 ohms and it's 500 ohms, which is exactly the stable load you're trying to put on this circuit for it to work correctly, selecting the range, and then upstream the regulator always sees the same resistance. So that's the essence of the Kelvin-Varley divider idea. Because of the way this works, you can actually have the same resistance values in both stages of these two Kelvin-Varley dividers, and it works out precisely. And I'm going to revisit this when I do this separate video on the voltage to current accessory, but what you end up with on here is that you have three terminals on this little metal box which plug into the three terminals on the output of the voltage source. And all you're doing is putting a resistor in series with the positive lead on the way out to a BNC connector, and then the minus input coming from the minus output here just goes straight through to the minus or ground side of the output connector. and that connector is isolated from the metal box. It's not electrically tied to it, but the chassis ground of the voltage reference source is connected to the metal box that surrounds this for noise shielding, without making the output circuit tied to earth ground in the process. It keeps it isolated. So you're either adding a 1000 mega ohm resistor in series with the output on the way of the voltage reference source on the way the output of this, or you're putting a 1 meg resistor in there. So to use this accessory, you're supposed to use the voltage reference source in its highest range, which is the 10 volt range, and assuming it's set to 10 volts, and then you're essentially putting a 1 meg resistor across that, because it's presumed that whatever you have tied to the output is some meter movement. Or it could even be a higher impedance, but in worst case it's a meter movement, like a old school volt-ohm meter or something like that, which have relatively low impedances. So compared to the 1 meg resistor here, you might as well not even have that meter in the circuit. It's such a small amount of resistance. So we're just calling it 1 meg ohms. You do Ohm's law on 10 volts divided by 1 meg ohms, and you get 10 microamps. So that's what it's supposed to do. You're supposed to get 10 microamps flowing through the output and through some device and back in, assuming that you have the voltage reference source set to 10 volts. Of course, you can dial it down and thereby get lower and lower voltages than 10 microamps. If you have the switch here in the other position, now you're going up to 1000 mega ohms, which is 1 giga ohm. I'm going to put that in here, 1 giga ohm. And you do the math, assuming 10 volts out here, and it comes out to 10 nanoamps. So that again is what this is supposed to do. It's either going to be a 10 microamp or a 10 nanoamp output current. And once again, because this is such a huge resistance, it doesn't really matter what else you put out here. It's going to be tiny compared to this, so you're getting 10 nanoamps or whatever lower value you're setting by lowering the voltage here. So that's how that works. I was kind of curious about it before, and that is the way they're doing it. It couldn't be simpler.